Hello students, good morning. I have uploaded a video on the proof of continuity theorem and lecture note which I believe we have discussed in our last interaction in a live class. So I hope that the proof is understandable to you, and I have also uploaded actually I had shared a already recorded video on infinitely many events, the concept of infinitely many events and Boris the statement and proof of Berel-Cantelli lemma. And that actually the video was recorded during the last semester in my MI 406. So there is some mention of something called convergence in probability. In that context, actually I had explained the importance of these two concepts. Now you need not worry about convergence in probability at this stage, but just focus on the concept of infinitely many events that I will probably repeat again in another class. So that link to that video has been already shared in our WhatsApp group of MS599. Now I am going to talk about the application of continuity theorem. This is just one of the applications, but there will be many occasions where continuity theorem and Borel-Cantelli lemma are used. This is a one exercise that I believe I have already mentioned in one of the previous live classes, that a coin is tossed repeatedly. What is the chance of getting all heads? In this problem, the sample space, as you know now, is that uncountable. Why? Because it consists of, here each outcome is a sequence of tosses. So we can write each outcome as a sequence xn, where xn is h or t. So the sample space is the set of all outcomes. So it is like collection of all such sequences, and we have argued using Carrington's diagonalization principle that this is an uncountable set. In this problem, we are interested in probability of computing the probability of a particular outcome, which is the outcome that all the tosses result in head. So it is a singleton set where the only element is the sequence where all position is head. Now this can be written as the intersection of n, where each n represents the event that the first n tosses result in head, and we are not giving any restriction on the remaining tosses starting from n plus 1 onwards. So I can write it formally as the collection of all the sequences where if the first n positions are head, and I am not mentioning anything about the other positions. Now it is a matter of verification that n is a decreasing sequence, that is n is a superset of n plus 1. I think you can easily verify that, because you see n plus 1, how will we write? We'll have to put the extra condition that xn plus 1 is head, but here you do not have that condition on xn plus 1. So n consists of also that sequence where first n position is head and the n plus 1th position is tail. But n plus 1 cannot contain that. N1 plus will contain only those sequences where all the first n plus 1 positions are head. So therefore you see n is a superset of n plus 1. So n plus 2 will be a superset of n plus 2 by the same logic, because then you are also putting a restriction on the n plus 2th position. So as n increases, n becomes smaller because you are putting more and more restrictions, so lesser and lesser sequences will be there. Now by continuity theorem, this is where the continuity theorem comes into play. Since n is the intersection of a sequence of decreasing events, therefore probability of n is limit of n. Limit n tending infinity, probability of n. Now what is n? N is a event concerning the outcomes of first n tosses of a fair coin. So I am saying this is a fair coin. When the coin is fair, we can assume all the outcomes to be equally likely. Now there are 2 to the power n possible outcomes in first n tosses of a coin. So when we are computing the probability of n, we are concerned only about the first n tosses, because this is a statement regarding the outcome of n tosses. So there are n tosses and 2 to the power n possible outcomes in n tosses. If each outcome is equally likely because the coin is fair, then probability of n where all first n tosses are head is 1 by 2 to the power n. Hence, what will be probability of a limit n tending infinity? I have not written it, but I think you can figure that out. This will be limit n tending infinity based and this is okay. Let me see. Let me try once more. Copy, yes. Paste. So limit n tending infinity 1 by 2 to the power n. Copy. So this is equal to 0. So I guess since it is equation area, the insert equation x to the power y to the power n. So you see. So therefore this is equal to 0. Now this is a very important result. So what we have shown is that probability of this event getting all heads in a sequence of coin tosses is 0. Now using the same argument, you can also argue that if instead of all heads I ask what is the probability of all tails, then this will be a t at every position, and the same argument goes through. Instead of h you write t. So probability of all tails is also 0. Now if I ask what is the probability of head and tail alternately, starting with head, so ht, so that would also be, you can write in the same way, right? Then an will be the first n positions are alternately head and tail, and no restrictions on the other. So you see the same argument will go on again and again, and you can prove that probability of every outcome of this random experiment has probability 0. Now this is a very strange result. What we are saying is that here the sample space is uncountable, but probability of every outcome, every singleton set is 0. Now you may question that now does it not violate the axiom 2, because axiom 2 says that probability of the whole set is 1, and axiom 3 says that when I have a sequence of disjoint set, probability of the union should be sum of the probabilities. Now the whole set can, for any set, the whole set is the union of the singleton sets. So in singleton sets where each singleton set consists one element. But now since the set is uncountable, so therefore this sample space here is a union of uncountably many point sets. But there you cannot apply axiom 3, because axiom 3 holds for countable additivity, that is countable number of sets. So it is very much possible that even when the sample space when the sample space is not countable, you can have a probability of every singleton set is 0. Now this phenomena has an analogy in measure theory. So if you recall what is a Lebesgue measure, the Lebesgue measure is that of BSGUE. Lebesgue measure generalizes the notion of length of an interval. You remember what is the Lebesgue measure of a point set or a singleton set? That is 0. In fact, Lebesgue measure of any finite set is 0. But what is the Lebesgue measure of any interval? That is a positive, b minus a. So you can, we have seen this in another measure theory, that it is possible that when the set is underlying set is uncountable, so you can have point sets having 0 probability, but uncountable subsets having positive measure. And of course, in measure theory, we will not say 0 probability, 0 measure. Now I leave it as a matter of just exercise for you to verify that if the sample space is countable, then this is not possible. That means if the sample space is countable, then it is not possible to assign probability to 0 to each and every outcome. So I leave it as an exercise to verify. One hint is that in that case, see what happens to axiom 2. Now this is the main distinction between the countable sample space and uncountable sample space, because in countable sample space, as this exercise has suggested, that it is not possible to assign 0 probability to all the outcomes, but in uncountable subspace it is possible that all outcomes can be given 0 probability, and therefore events which contain finitely many elements will also have 0 probability. That is possible, but that uncountable sets will have positive probability. Now, so this is the main difference. Now, probability on countable sets is called discrete probability. So this is the main difference between discrete probability and general probability. So I hope this argument is understandable to you. Please try the exercise. I will upload this video, upload more such videos. Thank you.